The mechanism of elimination reaction of alkyl halides may be either E2 or E1. E2 stands for a bimolecular elimination and E1 stands for a unimolecular elimination. Characteristics of E2 mechanism. First of all, molecularity of the reaction is 2. E2 stands for a bimolecular elimination. The reaction follows second order kinetics. R is equal to K into concentration of haloalkane or alkyl halide into concentration of base. The mechanism involves only one step. Abstraction of beta hydrogen atom by base. Removal of halogen atom as halide ion and formation of pi bond take place simultaneously. As an example, dehydrohalogenation of ethyl bromide using a hot alcoholic OH. The hydroxide ion abstract this hydrogen atom as a proton. The sigma electrons are used to make a pi bond. Simultaneously, bromine departed from the molecule as a bromide ion, giving CH2 double bond CH2 plus H2O plus Br minus. So, removal of beta hydrogen atom and halide ion take place simultaneously. During the reaction, hybridization of alpha and beta carbon atom changes from sp3 to sp2. So, E2 mechanism involves only one step. Removal of both leaving groups and formation of pi bond take place simultaneously. It is the most common mechanism observed in dehydrohalogenation of alkyl halides. Primary alkyl halides, secondary alkyl halides and tertiary alkyl halides undergoes E2 mechanism on treating with strong bases. In E2 mechanism, removal of both leaving groups and formation of pi bond take place simultaneously. Base abstract one of the beta hydrogen atom. In this process, hybridization of carbon changes from sp3 to sp2. Simultaneously, this bromine is removed from the molecule as a bromide ion. The alpha carbon also undergoes a change in hybridization from sp3 to sp2. So, both alpha and beta carbon atoms have a unhybridized p orbital perpendicular to the plane containing sigma bonds. Beta carbon atom have a pair of electrons in its unhybridized p orbit that overlap with a vacant p orbital on alpha carbon atom to form a new carbon-carbon pi bond. So removal of alpha bromine, removal of beta hydrogen and formation of a pi bond take place simultaneously. This carbon-hydrogen bond, carbon-bromine bond undergoes cleavage. A new pi bond is formed between alpha and beta carbon atom. E2 mechanism is a concerted process involving only one step. So in order to form alkene, the leaving groups must have anti-periplanar orientation. They must be trans with respect to each other. Hence the reaction is highly stereospecific. It can be illustrated with halocycloalkanes. For example, the cis and trans isomers of 1-bromo-2-methyl cyclohexane gives different products when subjected to dehydrohalogenation. This compound is a cis isomer. Cis isomer of 1-bromo-2-methyl cyclohexane. Hydrogen atoms are a common group. They are on the same side. Hence it is a cis isomer. So bromine is pointing towards the observer. On this carbon atom, one hydrogen atom is pointing towards the observer. And one hydrogen atom is pointing away from the observer. This bromine and beta hydrogen atom are trans with respect to each other. Similarly, here also second carbon also have a beta hydrogen atom with a trans orientation. That is bromine and beta hydrogen atom on a second carbon atom. These also have anti-periplanar orientation. Hence, when this compound is heated with alcoholic KOH, two isomeric alkenes are obtained. Along with 1-methyl cyclohexene, 3-methyl cyclohexene is also formed. It is a major product, around 75% is the yield. This is only 25%. It is a more substituted cycloalkene and hence it is a major product. In the case of trans isomer of 1-bromo-2-methyl cyclohexane, 1-bromo-2-methyl cyclohexane, only 6th carbon atom have a hydrogen atom with a trans orientation for dehydrohalogenation. In this compound, both 6th carbon and 2nd carbon atoms are beta carbon. However, 2nd carbon atom have a hydrogen atom on the same side of bromine. Therefore, it cannot participate in dehydrohalogenation. Only 6th carbon, it is also a beta carbon, have a hydrogen atom with a correct stereochemistry for dehydrohalogenation. Hence, trans isomer gives only one product when subjected to dehydrohalogenation. It is a 3-methyl cyclohexy The halogen atom and beta hydrogen atom must have a trans orientation. So double bond is formed between first and sixth carbon atom. This product is named as 3-methyl cyclohexene. The stereospecific requirement of the reaction. The leaving groups, that is beta hydrogen atom and halogen atom, must have a trans orientation. They must be anti-periplanar. Periplanar means almost planar. Anti means diagonally opposite. It is a stereochemical requirement of E2 mechanism. It have a significance in suitably substituted cyclic compounds, that is monohalogen derivatives of cycloalkanes, cis and trans isomers of 1-bromo-2-methyl cyclohexane behaves differently in dehydrohalogenation. E1 mechanism is observed only with tertiary alkyl halides in reactions using weakly basic nucleophiles. Characteristics of E1 mechanism. Molecularity of the reaction is 1. E1 stands for unimolecular elimination. Reaction follows first order kinetics with experimental rate law R equal to K into concentration of haloalkane. Here rate of reaction is independent on the concentration of base. E1 mechanism involves 2 steps. First step is slow and reversible heterolysis of carbon halogen bond to form a carbocation intermediate. In the second step, base abstract a proton from carbocation intermediate. For example, dehydrohalogenation of tertiary butyl bromide. First step, heterolysis of carbon-bromine bond to form a carbocation intermediate, that is a tertiary butyl carbocation. It is a rate determining step. In the second step, base abstract proton from tertiary butyl carbocation. To form the alkene. It is relatively fast. E1 mechanism is observed only in the case of tertiary alkyl halides and if the base is relatively weak. With strong bases like amide ion, alkoxide, like tertiary butoxide, etc., tertiary alkyl halides also follows E2 mechanism. The relative order of dehydrohalogenation of alkyl halides follows tertiary alkyl halides are most reactive, followed by secondary, then primary. If alkyl group is identical, alkyl iodides are most reactive, followed by alkyl bromide, then alkyl chloride.